You can see that it's 6:58, 50, 26, 27 seconds in London, September 18th. A non-orientatable surface will eventually drive you insane. I'm just looking at my Möbius strips again, and the topology and the knot theory, and specifically the Jones polynomial, because I was watching an Ed Witten lecture on string theory and topology, and there's a connection. Well, where to start with all this mumble jumble? Well, these are two special knots I found hidden in the Möbius strip. They're what I call braid knots. So we got to start with a Möbius strip. It's a strip of paper. Normally a Möbius strip has one flip, but I've had it three flips because they're more complex, more enjoyable to study. It's a Möbius strip with three flips. When you cut it, it has one edge, one surface. When you go in this direction, you end up back where you started. It's not non-orientatable. When you cut it in the middle, you add an extra edge. That edge an extra boundary. So there's three twists. So when you cut it in half, it goes to 8 twists, 2 edges, 2 surfaces. Because the number of twists afterwards falls on an equation that I found, which is 2n plus 2. So 2 times it by 3 is 6 plus 2 is 8. So that's the Möbius strip. Here's what it looks like when it's almost cut down the middle. You can see it's not quite parted right here, but we'll part it right now. So we'll just tear it, and you can see what it leaves behind. It leaves behind a trefoil knot. Now you'll notice where it crosses itself, the edges contact each other. So if you add a half snip and let those planes intersect, it makes what's called a framed knot. And it takes 6 crosses to flatten the Möbius strip, so then it all stands up like a fence. So here is now there's one. Now the braid group, what you got to do is orientate it into a coil, and then if I show you on the video so you understand, what happens is that you lengthen it, so this bigger loop here, so this bigger loop gets pulled around and turned inside out. And then you can see it makes the braid group. And there's only 2 examples. So and what is interesting is that now you have one edge on the bottom, one edge on top, and the boundaries. You have the black boundary on the outside. On the inside, it's all the white boundary. Those knots are unique. Now, when I did the Jones polynomial for that one there, you can see the function. But I did the Jones polynomial for this one. So remember, there's two braid groups. That one there is this one, and you can see how we have 2 crossings coming over the 3. You can just see how that knot is formed. But this knot here, I've drawn it more simply. When I do the Jones polynomial there, Vt equals 1. So we get the unknot. That just ends up as an unknot. So look, irregardless of what configuration the loop of string is in, if you count the crossings correctly, you can tell if it will be untangled or not. And then if I pull this apart, you can see that's just an unknot. It's a loop of string. So based on the Jones polynomial, we know that this one makes the unknot. So that we know, and I've worked out the Jones polynomial for that braid, and I'll call it braid K, as opposed to K sub 1 for this one. We'll call this one here K sub 1. We've got to give them names. I don't know what the names are. I did discover these knots. So here is this one here. It's been laid down in the correct crossings, and there should be a knot left behind if the Jones polynomial is correct. And then I'll tell you what's incredible about that. So I pulled it off. She's a beaut. Look at that. I just pulled it tight. Oh, lovely. That's the trefoil knot. Look. So here is the trefoil knot that's left behind. Now here's what's amazing about that. What's amazing about that is because when I had this coil, there's one orientation that I put it in that makes the unknot, but this one has the knot, and they have the same etiology. They are both formed from a 3-flip Möbius strip, cut down the middle, organized into a coil with 4 loops, the fifth loop is made extra longer and flipped around itself, then you find the right orientation that you have two different braids. Now, I could not have made a mistake. I might have made a mistake, but I don't think I made up a random coil of paper and got a crossing wrong. I didn't, for example, cut it here and make some other crossing and then put it back together. I don't think I did that. Now, although I haven't found this orientation tonight, I know it exists because I remember doing it. But I am just absolutely floored by that because that is an anomaly. Like, I don't understand it. It's not understandable to me because... But I'm going on the premise that this knot is just an orientation of this braid. Like it's not a mistake. Like this is one of my Möbius strips I've organized into this knot. There's only two examples, and all the rest of the groups they're either trefoil knots or they're figure-of-8 knots. You can see all the different knots that I found. See, there's lots of this little family with the trefoil, with a non-alternating figure-of-8 knot, and there's lots of this group with like a trefoil knot. There's a lot of them. There's maybe about 80 or so. And there's one knot that I found that relates to the Lorentz attractor from chaos theory. It's this knot here. And that one there doesn't make an unknot. There's a knot left behind. You can see the Jones polynomial. Oh, it's doing my head in. Because I gotta find that knot. And I can't get it orientated the right way. But I don't want to believe that I made a mistake and I just made a crossing and then put it back together and then wrote down a bogus knot notation. I made up the knot notation for myself until I actually decided to read about knot theory. So that's where I'm at with Möbius topology and knot theory.